So moving from fluorine, I'll take another complex molecule where it won't be that easy to write the electronic dot structure. And we are going to discuss in that case scenario what we need to do. The example here is, it's a very interesting example, is of dinitrogen monoxide. Dinitrogen, there are two nitrogen and monoxide. Is that right? So to write down the electronic dot structure for this molecule, again I'll start from the number of valence electron. The number of valence electron for dinitrogen monoxide is, there are two nitrogen, and each of those nitrogen contributes 5 valence electron. How do I know? Again, if I look at the periodic table, nitrogen belongs to the 5th group. So that means it has 5 valence electron. Or if I look at the electronic configuration, the electronic configuration is 1s2, 2s2 and 2p3. So in the second shell, which is the outermost shell, it has 5 electrons. So that means there are 5 valence electrons. And there is only one oxygen atom, and that oxygen atom has 6 valence electron belonging to the 6th group. So in total, in N2O molecule, there are 2 times 5 is 10 plus 6 is 16. There are 16 valence electron. So while writing the electronic dot structure for dinitrogen monoxide, I need to arrange 16 valence electron around these 3 atoms in this molecule. Okay? In the next step, I need to develop the, I need to determine which is the central atom. For central atom, as I told you, first we have to look into the number of atoms. The second, we have to look into the electronegativity. The electronegativity is the most crucial one. Okay? The central atom invariably is an atom which is of lower electronegativity than the terminal atoms. So when I look into the electronegativity scale and look at the periodic table, nitrogen is to the left of oxygen. That means nitrogen is less electronegative than oxygen. And oxygen has an electronegativity on the scale 3.5 and nitrogen is 3. In that case scenario, nitrogen is a central atom. I again repeat, because nitrogen is less electronegative, it is a central atom. And then what I have to do is, I have to arrange the terminal atoms around the central. So since there are 2 nitrogen atoms, I can choose any one of them. So it doesn't make a difference in there. Okay? So you have 1 nitrogen atom as a central atom, and then you have another nitrogen atom as a terminal atom, and an oxygen atom as another terminal atom. Now in the third step, what I need to consider is that the terminal atoms, their octet is complete. Okay, so over here you have nitrogen and oxygen. So I have to arrange the electrons in such a way that their octet is complete. So let's start from oxygen, since oxygen is the most electronegative out of these two here. So when I arrange electrons in 3 pairs, that means I'm including 6 electrons here, 3 pairs here, and there is 1 bond pair here. So in total there are 8. So now the octet on the oxygen atom is complete. The octet is complete here. And then the other nitrogen atom. This octet is complete here. It's 2, 4, 6, and 8. So then I have to count the number of electrons which I've already accounted for. 8 here and 8 on this side. So 8 plus 8 is 16. So I've accounted for 16 valence electron. And how many valence electron we have when we begin? It's 16 valence electron. That means I have accounted for all the valence electron which are assigned to N2O. I don't have any extra electron to put on the central atom. So that's what it is. So in the fourth step, I have to look for whether the central atom octet is complete. Let's see that. There are 2 here, 1 and 2. There are 2 there, 1 and 2. So 2 plus 2 is 4. So on the central nitrogen atom, there is only 4 electrons on it. Its octet is incomplete. So I need to rearrange the distribution of the electron in such a way that the octet on each of these 3 atoms is complete. So how I can do that? One way of doing that is that I bring this lone pair of electron and convert this lone pair of electron as a bond pair electron. I can do that. So once I do that, so let me rewrite it again. Then what we have is we have 2 bonds between the 2 nitrogen atoms. There is a double bond. How this double bond, how this second bond has come from? Because this pair of electron comes in between the 2 nitrogen atoms. This means this lone pair here has now become a bond pair. So there is a double bond in there. And then I'll put the other electrons the way they were. Okay. So again the number of valence electrons remains same. 4 plus 4 is 8, plus 2 is 10, plus 6 is 16. So I have not added or subtracted any of the valence electron. The octet on this nitrogen is complete. 4 plus 4 is 8. The octet on this oxygen is complete. 6 plus 2 is 8. Let's see the octet on the nitrogen atom is complete or not. So it's 4 here and 2 there, 6. The octet is still not complete. So how I can complete this octet? I can do that when this pair of electron here, which is a lone pair, gets converted into a bond pair and comes in between these 2 nitrogen atoms. This moves from here. That means this here moves there. So when I do that, then I have a triple bond between the nitrogen atom. So the octet on this nitrogen is complete because 3 bond means 6 electrons. So there are 3 bond pairs and there's is 2 here. So the octet on this nitrogen is complete. The octet on the oxygen is complete. And let's see the octet on this nitrogen, the nitrogen is complete or not. It's so 6 on this side, 2 on this side, and that's fine. And this is an electronic dot structure for N2O, and the octet is complete for each of the atoms, whether it's terminal or for the central atom. But here comes the question. Why only these electrons are getting converted into a bonded pair? Why only these? Why not these electrons? The electrons which are on the oxygen are getting converted from being a lone pair into a bond pair. What I'm asking is, what I'm saying is, there is equal probability that the electrons on the oxygen, the lone pair of electron on the oxygen, get converted into a bond pair, get converted into bond pairs. What happens then? Means no longer the lone pair on the nitrogen are getting converted into the bond pair, but the electrons, the lone pairs on the oxygen, getting converted into this one. Okay? What will happen? We are going to get a structure which will look like this. Right? Equally possible. These 2 pairs are getting converted into the bond pairs between the nitrogen and oxygen. So as a result, you have a triple bond between the nitrogen and oxygen and a single bond between nitrogen and nitrogen. On the first structure, so I'm going to label it first structure, and this is a second structure. Okay? So the difference between these 2 is, in the first structure you have a triple bond between nitrogen and nitrogen. In the second structure you have a triple bond between nitrogen and oxygen. Okay? Yeah, pretty much possible. But then, is this the only 2 possibilities? Is there any other possibility too? The answer is yes. What is that possibility? The possibility is that one lone pair on each of the terminal atoms, gets converted into the bond pair. This lone pair comes in between these two nitrogen atoms. This lone pair on the oxygen comes in between nitrogen and oxygen. In that case, what is the structure we are going to get? We are going to get a structure where we have a double bond between nitrogen and oxygen and a double bond between nitrogen and nitrogen. And the structure, the electronic dot structure, will look like something like this. Want to emphasize here is I'm not changing the number of valence electron. It remains constant in each of these three structures. I cannot do that. I cannot add electron or I cannot remove electron from the molecule. So you can count here. 4 plus 4 is 8, plus 2 is 10, and then plus 2 is 12, and plus 4 is 16. There are 16 valence electrons on that. Same is here. It's 8, 10, 16, and the number of electrons in there. 6 and 8, 6 is 14, plus 2 is 16. So I haven't changed the number of valence electrons. So that means whatever we have discussed in this methodology, we are getting three structures which looks to, at this time, equally probable. But which is the actual structure for N2O? Which is the actual structure, and how we can find the real structure for N2O? So for doing that, we will move to another concept, that when that kind of dilemma, that kind of structures we get, where we get multiple structures for a single molecule, how we can determine which structure is the most probable structure for that molecule. To solve this, we are going to discuss another concept which is called the formal charge. So we are going to calculate the formal charge on each of the atoms of a molecule to predict which out of these three structures is the dominant structure, is the most probable structure. And that we are going to do it with the formal charge. So for doing that, I'm going to rewrite all these structures and then going to determine which is the most probable structure. So for N2O, we got three structures. In one case scenario, there is a triple bond between nitrogen and nitrogen and a single bond between nitrogen and oxygen. In the second case scenario, we have a single bond between nitrogen and nitrogen, whereas a triple bond between nitrogen and oxygen. So remember to put the lone pair of electrons to complete the octet and to complete the electronic dot structure. So structure 1, structure 2, and in the third case scenario, you have equal distribution as far as the sharing of lone pair of electrons is concerned, and you have double bond between nitrogen and oxygen and nitrogen and nitrogen. So the octet should be complete, so you can arrange the lone pairs in there. So you have three structures. So my problem here is to find out which is the most probable structure. So the methodology which we are going to use is to calculate the formal charge on the atom which constitutes that molecule. This means we need to calculate the formal charge on this nitrogen, formal charge on this nitrogen, and formal charge on the oxygen atom, and then we'll arrive to a conclusion. So how we can calculate the formal charge? the formal charge, I can write it in an abbreviation in parenthesis FC, which is the formal charge. It is equal to the number of valence electrons on an atom for which we are calculating the formal charge. So when you say I want to calculate the formal charge on this nitrogen atom, how many number of valence electrons are there before they have formed the bond with the other atoms to form the molecule. So this is of an atom. Okay, for nitrogen this will be 5. Okay, minus the number of lone pair of electrons, or I'll say, I won't say lone pair, I'll say non-bonded electrons, just to avoid confusion, although it's right, but just to avoid confusion, I'll say the number of non-bonded electrons, not pair, non-bonded electrons, right? The electrons which are not participating in the bond formation, minus half, and I'll explain later on why half the number of bonded electrons, So if you just look into this whole formula here, it is basically the number of valence electron before the formation of a bond minus the number of valence electron on an atom after it has formed the bond with the other atom to form the molecule, before and after, right? Now, minus the number of non-bonded electrons and minus half the number of bonded electron. Why there is half here? And it's very simple to get to this, because the formal charge we calculated for the molecules which are covalent in nature, and covalent nature means a bond which is formed by the sharing of electrons, where the electrons are being contributed by each of the atoms which are forming the bond. So like here, the nitrogen and oxygen, there is a single bond. So I'll show these two electrons in there, right? So one of the electron is coming from nitrogen, the other electron is coming from oxygen. It's as simple as that. So whenever there is a bond formation, whenever there is a covalent bond, one atom contributes, say for example, 1 electron, the other atom will also contribute 1 electron. So there is an equal contribution from both the electrons. So that means if I'm considering these two electrons which are bonded electrons, then half is coming from nitrogen and half is coming from oxygen. Here, how many bonded electrons I am seeing? I am seeing 6 bonded electrons. Out of this 6 bonded electrons, 3 are coming from one nitrogen atom and 3 are coming from the other nitrogen atom. Half is coming from one atom, half is coming from another atom. That's the reason you have an half in there. So that's how you remember that it is half the number of bonded electrons. So this is the formula, and it's very easy. So let us calculate the formal charge on each of the atoms for each of the structures here. So let's go with the first structure. I'm going to use the different color pen to calculate the formal charge. So let's calculate the formal charge for the first nitrogen atom, this nitrogen atom. So this will be equal to the number of valence electron before this nitrogen atom has formed a bond is 5. Is that very simple, is that right? Before it forms a bond, the number of valence electron on this nitrogen atom is 5, minus the number of non-bonded electrons. So now if I see the electronic dot structure, the number of non-bonding electrons for this nitrogen is 1 and 2. So there are 2 non-bonding electrons. So I'm putting 2 down there. Minus half, so I'm going to write half. And in parentheses, I'm going to write the number of bonded electrons. So how many bonded electrons I'm seeing? 1, 2, 3, 4, 5, and 6. So there are 6 bonded electrons. Okay? So if I solve it, then what I get is 5 minus 2 minus 3 equal to 0. So that means this nitrogen here has a formal charge of 0. Okay? So let's calculate the formal charge for this nitrogen atom, the terminal nitrogen atom. For clarity's sake, I'm writing T as a subscript here. So that, not T, sorry, the C, to demonstrate that I'm talking about the central nitrogen atom, the central nitrogen atom. So what is the formal charge on it? Again, the number of valence electron will be 5 minus the number of non-bonded electrons. And if you see on this nitrogen atom, there is no non-bonded electrons. There are no lone pairs here there. So it is 0 minus, for this oxygen atom, if I see it here, for this nitrogen atom, if I see here is the number of bonded electron is 6 from this side and 2 from this side. So in total there are 8 bonded electrons. I again repeat, 6 from this side, 6 from this side, and 2 from this side. All these are bonded. So I'll write half. In parentheses, I'm going to put 8. So if I solve it, this becomes 5 minus 4 equal to 1. 1 positive. All right? 1 positive. So the charge on this nitrogen is plus 1. The formal charge, not the actual charge, the formal charge. Okay? Now, in the same way, we are going to calculate the formal charge for the terminal oxygen atom. For that, the number of valence electron is 6 minus the number of non-bonded electrons. Again, what I'm seeing is 6. 1, 2, 3, 4, 5, 6 minus half of the bonded electrons. So how many bonded electrons I'm seeing on this oxygen atom? There are only 2. So I'm putting 2 in there. When I solve it, what I get is 6 minus 1. That means negative 1. So that means this oxygen has a formal charge of negative 1. Okay? So this is the formal charge on each of the atoms for this structure, 0, plus 1, negative 1. Okay? The same thing we are going to do for the other structures, and I will be a little bit quicker here. So what is the formal charge on this nitrogen atom for the structure 2? So for this nitrogen, the formal charge is 5, the number of valence electron, minus the number of non-bonding electrons. There are 6, 1, 2, 3, 4, 5, 6, minus half of the bonding electron. I'm just seeing 1 bond. That means there are 2 bonding electrons, 2. So what I get is 5 minus 6 and minus 1. So that means negative 2. That means a negative 2. Minus 7, 6. So this is a negative 2 here. For this nitrogen atom, what is the formal charge? Nc. And that is 5 minus 0, because there is no non-bonding electrons, minus half of the bonding electrons. 6 from this side, 2 from this side is 8. So this will be 5 minus 4. So that means a positive 1. So the formal charge on this nitrogen is a positive 1. And for the oxygen, the formal charge will be the number of valence electron is 6 minus the number of non-bonding electron. You can see here there is 2 minus half of the bonding electron. You see triple bond, so that means 6 electrons. 6, so in total what you get is 6 minus 2 minus 3. You solve, what you get is positive 1. You get a positive 1. So these are the formal charges for the structure 2. In the same way, you can calculate for the structure 3. For the structure 3, the formal charge on the terminal nitrogen atom is 5 minus 4 minus half of the bonding electron. There are 2 bonds, so that means 4. So that makes 5 minus 4 minus 2, so that means a negative 1. So there is a formal charge of negative 1 on this nitrogen atom. For the other nitrogen atom, which is the central nitrogen atom, the formal charge is 4 minus 0, there is no bonding electron, minus half of the bonding electron. There are 4 bonds, 1, 2, 3, 4. That means there are 8 bonding electrons, so what you get is 5 minus 4, so that means a positive 1. So this is positive 1 here. And what is the formal charge on this oxygen atom? It is 6 minus, there are 4 non-bonding electrons minus half. There are 4 bonding electrons. So what I get is 6 minus 4 minus 2 equal to 0. 0. So these are the formal charges for this molecule. Once you have done that, now we have to figure out which is the dominant structure, which is the structure which is going to contribute more to the electronic dot structure, which is the actual electronic dot structure. For that, we'll consider 3 points, 1, 2, and 3. The first point is the most dominant structure or the actual electronic dot structure of a molecule is a structure where every atom in the molecule have 0 formal charge, has a 0 formal charge. So when I look into these 3 structures, there is none of these structures is there where every atom which is there part of that molecule have a 0 formal charge. Here there is only one nitrogen which has a 0. Here it's another oxygen which is 0. Here none has the 0. So the first is not solving our problem. The second rule is that the structure is a dominant structure where majority of the atoms have 0 formal charge, majority of them. Okay, so that means if I have structure A and B, and in structure A you have 2 atoms which have 0 formal charge, in structure B you have just 1 atom with formal positive charge, then structure A is the dominant structure and structure A is the actual electronic dot structure. So when I look for this thing under these circumstances, then definitely structure 2 is a structure where there is no atom which has a 0 formal charge. So we can actually remove the structure 2 from consideration because there is none of the atom has a 0 formal charge. That's what I'm looking for. Is that right? So that means the electronic dot structure for N2O is not 2 because none of the atoms here has a 0 formal charge. 2 negative plus 1 plus 1. They don't have a 0 positive charge. I'm looking for the 0 formal charge. Is that right? But when I look into structure 1 and structure 3, then I definitely have at least one atom which has a 0 positive charge. A 0 positive charge. So that means structure 1 and 3, keeping the second in mind, is equally probable, but only one can be a possible structure. So for that, I'm going to look into the third rule, which says that a structure is a dominant structure where the most electronegative atom has a negative formal charge associated with it. So the most electronegative atom should have a negative formal charge associated with it. So the actual electronic structure, electronic dot structure, will be a structure where the highest highest electronegative atom will have a negative formal charge. Okay, will have a negative formal charge. So when I look into the structure 1, then oxygen here has a negative formal charge, one negative formal charge, right? And when I look into the structure 3, then it is the nitrogen which carries a negative formal charge. And when I compare nitrogen with oxygen, and oxygen is to the right of nitrogen, then oxygen is more electronegative than nitrogen. Oxygen has an electronegativity of 3.5, nitrogen has an electronegativity of 3.0. So oxygen is more electronegative. So that means oxygen should carry a negative charge, not nitrogen. So when I look at structure 1, the oxygen here is negative charge. It has a negative formal charge, whereas for structure 3, it's the nitrogen which has a formal negative charge, and oxygen doesn't have a formal negative charge. It has a 0 formal charge. So that means the structure 3 won't be a dominant electronic dot structure, won't be a contributing structure. That means N2O will have this electronic dot structure. So I'll redraw the electronic dot structure for nitrogen. In fact, I'll draw it at the top. The electronic dot structure for N2O is where the two nitrogen are bonded by a triple bond, and the nitrogen and the oxygen are joined by a single bond, and you just arrange the non-bonded electrons or the lone pairs around it. So this is the actual electron dot structure for N2O. It's a little bit complex, and there are more such molecules which are complex, and we are going to discuss it in our next lecture about some examples where the octet on the central atom is extended. Till now, keep looking for the link after this video, which will take you to an activity which will have some question related to what we have discussed to get to whether you got the concept right, and rest we can discuss in our class. Thank you very much.